Hello everyone, my name is Marco Cerezo and I will be presenting my work on variational quantum fidelity estimation. This work was made in collaboration with Alexander Poremba, Lucas Cincio, and Patrick Coles at Los Alamos National Laboratory, where I'm a postdoc currently. This work was also recently accepted in Quantum, for which we're very happy. It is unfortunate that we did not get to meet at APS March Meeting this year, but hopefully next year we'll get to meet face to face. So without any further ado, this is the outline of our main results. First, I'm going to present our contributions to quantum information theory, which are novel upper and lower bounds for the quantum fidelity between two quantum states. And as I'm going to explain, those are based on the idea of projecting one of the states and truncating it into the subspace associated with its m largest eigenvalues. Then we're going to present a variational algorithm that we call variational quantum fidelity estimation. And I'm going to show how these bounds that we're presenting compare to other state-of-the-art bounds from the fidelity by doing numerical implementations for some low-rank states. Finally, for this algorithm that we're presenting, we did a complexity analysis and we showed that the problem of estimating the fidelity when one of the states is low rank, which is the case that we're going to be interested in, is classically hard. So the motivation is that nowadays we have quantum computers, and those quantum computers are essentially going to be preparing impure quantum states. And now this could be intentionally because we're studying thermal states, or it could be unintentionally because we have, for instance, quantum noise like T1 and T2 processes. So the question is, if we have two quantum states, and those two quantum states say they're from the same process, so they should be the same, how can we verify and characterize that our quantum computer is doing what it is supposed to be doing? Well, we can always compute the quantum fidelity, which is going to give us an idea of how close those two states are. And the quantum fidelity is just defined right here. And you can think about it as the one norm of the matrix defined by the square root of rho and the square root of sigma. Now, this quantity is really hard to compute. If you have a classical description of those states, you know that the size of the density matrix is going to grow exponentially with system size. So computing the fidelity classically is going to be exponentially hard. And we also know that there is no quantum algorithm that will give us exactly the fidelity. And it's really simple to see this. And this is because the fidelity is a nonlinear function of our quantum states. So we cannot have a quantum algorithm to exactly compute it. So the next best thing is trying to bound the fidelity, give upper and lower bounds for the two states that we're interested in. So our contribution comes from taking the subspace, and I have defined here, Ri and the kets Ri as the eigenvalues and associated eigenvectors of rho, and we can define a projector that is going to project into the subspace of the eigenvectors of rho with m largest eigenvalues. With this, we can define the subnormalized states, rho, and m, which are projected into this subspace, where here the eigenvalues of rho are ordered in decreasing order. And from here, we can define the truncated fidelity. As you can see, it's just as the fidelity, where instead of taking rho, we just take this projected and truncated states, rho m, and we can also define a truncated generalized fidelity, which is essentially the same as before, but with this additional term here that we're adding up. Now, the truncated generalized fidelity was inspired by the generalized fidelity presented by Marco and Mitchell. And what we have managed to show is that the truncated fidelity and the truncated generalized fidelity are actually bounds for the fidelity that we're interested in. So not only this, because we can decide how many eigenvalues we want to take in this projector that we have defined, we have not just bounds, but a collection of bounds with them that we just call the fidelity spectrum. And moreover, we can also show that these bounds get monotonically tighter with them, which means that as you start to increase the size of the subspace in which we're projecting, then these bounds will get monotonically tighter. The main idea behind this is that if we have a state that, say, like is low rank or its spectrum is exponentially decreasing, then most of its information is going to be encoded in the subspace of its largest eigenvectors. So this is what we call the truncated fidelity bounds. Now the question is, what do we gain with this? Is there some advantage of using the truncated fidelity bounds versus the fidelity? Because we still have these quantities right here that we need to compute. So if we just take this one norm, we can always expand it and just write it in this form, where we have defined a matrix T, which in this case is going to be an m times m matrix that has the following really nice properties. First of all, it's going to be positive semi-definite. And second of all, its matrix entries are given by just the square root of the eigenvalues of rho and the matrix elements of sigma in the eigenbasis of R. So why is this important? Why do we care about this quantity? Well, because if we want to compute the truncated fidelity bounds, now we have broken up the problem of computing this one matrix norm into a problem where we just have to be able to know the eigenvalues of R and these matrix elements. Because if you see from these definitions, the eigenvalues of R are used to compute the matrix elements of Tij and are used to compute this term, while the matrix elements of sigma in the eigenbasis of R completely defined along with the eigenvalues of R, the T matrix, and this term right here. So now we have transferred the problem to computing the fidelity to the problem of computing bounds on the fidelity. And now finally, in order to get those bounds, we need to compute these quantities down here. And the thing is that T matrix is just M times M, where we get to choose what's the size of this matrix, what's the size, the dimension of the subspace that we're taking. Now, we still have this square root that we cannot compute with a quantum algorithm, but if the T matrix is small enough, we can classically diagonalize this matrix. So essentially, our algorithm is reduced to trying to compute these quantities right here. And this is where our algorithm, the variational quantum fidelity estimation algorithm, comes in. So the first part is that this is algorithm that is divided into three parts. The first part, what we need to do is we need to take rho, which is going to be a quantum state that we assume that we have a quantum description for it. We can prepare it on a quantum computer. And with a hybrid quantum classical algorithm known as variational quantum state diagonalization that was developed by Ryan LaRose and other collaborators at Los Alamos National Laboratory, this algorithm, what it does is that it will output the largest eigenvalues of our state rho, and it will output gate sequences that will prepare its associated eigenvectors. So the first thing that we need to do to be able to compute bounds on the fidelity is be able to compute the eigenvalues and prepare the eigenvectors. The second step of VQFE is taking those results from having diagonalized rho and just computing the matrix elements of sigma in the eigenbasis of rho. So for this, we have a hybrid quantum classical computation where we can get those matrix elements. And essentially, if we have quantum circuits that are able to prepare the eigenvectors of rho, we just need to prepare a superposition of this form and use a swap test, and we will be able to get all of these matrix elements. So here you can see that this is schematically the T matrix that we're so interested in. And finally, we can just classically diagonalize the T matrix and compute upper and lower bounds on this fidelity. And once again, this is a procedure that we get to choose how hard it is. We get to choose what's the dimension of the subspace that we're projecting in. So what are the numerical implementations that we're doing, and how do we know if our bounds are good? Well, we're comparing our truncated fidelity bounds with what we call state-of-the-art bounds of the fidelity. In this case, they're known as the sub and super fidelity, and they have been defined in this really nice paper down here. And as you can see, there are two quantities E and G that have been defined in this way, and they are upper and lower bounds for the fidelity. Now, the thing about this bounds is that in order to compute them, you need to have, if your state rho is on n qubits, you need to have 4n plus 1 qubits to be able to compute the sub and super fidelity, whereas our bounds can be computed with just 2n qubits. So not only we have reduced the number of qubits, but as I'm about to show, our bounds are usually tighter than the sub and super fidelity bounds. So for our first implementation, we just take two quantum states, rho and sigma. We randomly generate a state sigma, and we create a low-rank state rho. So what we have done here is that we have computed the actual fidelity, which is this red solid line that is right here. This is a 3-qubit and 6-qubit state where the rank of rho is given, in this case, this has a rank 4, and here it has rank 8. And what we have done is that we compute the sub and super fidelity, which are these dashed lines. So here I have fidelity as a function of the dimension of the subspace, or the number of eigenvalues that I'm putting in my upper and lower bounds. So evidently, the sub and super fidelity bounds are constant, and they will not depend on them. And our bounds, which are the TFB, truncated fidelity bounds, get tighter as we increase the number of eigenvalues and eigenvectors in this truncation of rho. And we can see that in both cases, with very small number of eigenvalues, or that means very small m, our bounds will be tighter than the sub and super fidelity bounds. And moreover, we have also this gold line, which are called certified bounds. I will not get into detail, but essentially these bounds take into account errors that we can have during our variational algorithm. We have also shown that our bounds can be used to detect quantum phase transitions. So here we have prepared and simulated the thermal state of an Ising chain of 8 spins, one having a transverse field. And the fidelity is used for phase transitions because near phase transitions, your state is going to change. So the fidelity, if you're comparing states as you're changing your parameter, in this case, the field H, will have a dip near what would be known as phase transition. So here you can see that once again, dashed lines are sub and super fidelity for different value of the field, and our bounds, as you increase m, they just get monotonically tighter towards the true fidelity. So our bounds will give a better estimation of where this phase transition occurs. And finally, I don't want to use too much time. We have a complexity analysis where our problem is we want to estimate the fidelity for what we call the low rank fidelity estimation. So the input is we have two circuit descriptions of two quantum circuits, U and V, that will prepare rho and sigma on n qubits or on a subset of all of those qubits that are initially in the zero state. And we have a parameter gamma. And the promise is that one of those states is low rank. Here by low rank, we mean that the rank of rho is poly n. And what we want to get is approximations of the fidelity up to some additive accuracy gamma. And what we have managed to show is that this problem of estimating the fidelity for low rank is DQC1 hard, which means that classically estimating the fidelity is classically hard. So our algorithm is giving us an advantage because precisely for low rank states is when the case when our bounds are going to be good and when we don't have to make m, the number of eigenvalues and eigenstates, too large. So just to recap, these are our main results. We have provided novel upper and lower bounds for the fidelity based on this idea of truncating one of the states. We have proposed a variational algorithm to compute those fidelities. And not only that, we have shown that the number of eigenvalues, which is essentially the dimension of the T matrix, does not scale exponentially with n, and that computing those this fidelity is a classically hard problem that we can solve with our VQFE, variational quantum fidelity estimation algorithm. And with that, thank you very much for your attention, and I hope to see you all at the next APS March meeting.